Alright, now let us do something about vector analysis, which is of great practical importance whenever you look at vectors of different kinds, vectors of different vectors in a given problem. And here is the general problem. Suppose I give you in 3-dimensional space a vector A and another vector B, arbitrary vector B in this fashion. I could ask the following question: how much of this B points along A? What is the projection of the vector B along A? What is the component of B along A? That is a question which arises in practice very often. Well, one way to do this would be to say I write B in Cartesian coordinates, Bx, Ex, By, Ey plus Bz, Cz. Similarly for A, and I take the overlap between the two, which is B dot A, and try to discover how much of B is along A using the fact that Ex dot Ex is 0 and Ex dot Ex is 1, Ex dot Ey is 0 and so on. Okay. That is one crude way of doing this, but there is a more elegant way of doing this, and that is what I would like to show you today. If I project this vector onto this vector, it is equivalent to saying I draw a perpendicular from there, and let me draw a better figure. Here, if I project this B onto A, that is like saying draw a perpendicular, and this length here is the projection of B in the direction of A. Now we can easily write down what that is, because if the angle between these two vectors is theta, then B dotted with the unit vector in the direction of A, in this direction A sub A, is of course the magnitude of this length here, and the direction of this segment, line segment, is along EA. So this here is EA. This is a scalar, this is a number, and that multiplied by the unit vector will give me the actual vector. So that represents this vector with the tip ending here at this point. So what I have done is to write this B vector as B along A, so let me call it B parallel, and the rest will be of course perpendicular to A, and let me call that B perpendicular. So this is along A, and this is perpendicular to A. That could be in a plane perpendicular to A anywhere. The perpendicular component could be anywhere, because B could point anywhere starting with its tail here. Okay. So the target now is to write down formulas for B parallel and B perpendicular, and B parallel is extremely simple to write down. This is equal to B parallel. Of course, if you do not like me to write the unit vector in the direction of A, it is easy to see that this by definition is equal to the vector A divided by the magnitude of A, because the vector A is the magnitude of A multiplied by the unit vector in its direction. So I can write B parallel to be equal to B dot A times A divided by A squared, because there is one A coming from this unit vector and another A coming from that unit vector. So I have a formula for B parallel, which is very straightforward. Now what can B perpendicular be? Well, it is clear that B perpendicular is B minus B parallel. So it is immediately obvious that I write an identity. This is identically equal to, let me write it as A dot B, A over A squared, plus the vector B minus the same thing, over A squared. So this is B parallel, and this part is B perpendicular. And the question is there some simple formula for this portion which is written in a more compact way than in this rather messy notation? It is just an identity. All we have done is to resolve this vector into two components, one of which is along A and the other is in a plane perpendicular to A somewhere in this direction. In this case, in this figure, it would be something like that. That would be the perpendicular component, and the two added up would give me this vector B. So this is called the resolution of a given vector B along some other vector A, any other given vector A. And what we are seeking is a formula for this portion, which makes it look like a very straightforward, simple way of writing this resolution here. Now notice I have not chosen any specific coordinate frame here at all, because it is not necessary. We are working entirely in terms of dot and cross products, and that is enough. Okay. Now what is the next step? Well, that requires a little bit of an identity, and I am going to spend a little bit of time talking about this identity. That is the following. But before that, I need to do the following. I need to point out that in the Cartesian basis, Ex, Ey and Ez were unit vectors, and these vectors satisfied the property Ax dot Ex is equal to Ey dot Ey is equal to Ez dot Ez equal to 1, and moreover they formed what is called a right-handed system of unit vectors, in the sense that Ex cross Ey is equal to Ez, which says that here is x, here is y, here is z. So if you took the unit vector in this direction and you rotated it through 90 degrees up to Ey, then the screwdriver, a right-handed screwdriver, would move in the direction of Ez. So that is a right-handed coordinate system. This forms a right-handed triad. Of unit vectors, and so on. This is in cyclic permutation. Ey cross Ez equal to Ex and Ez cross Ex equal to Ey. I should mention here that in 3 dimensions, once you have x, y, z in cyclic permutation, then you can actually write down the value of any cross product of two vectors the way I wrote down for A and B, but it is useful to have a mnemonic device for this, and the one that is most common is to write a thing like, and this is a standard thing in textbooks, if this has components Ax, Ay, Az, and similarly for B, then this is written as the determinant I, J, K, Ax, Ay, Az, Bx, By, Bz. I am going to put this in quotation marks because it is not a great idea to write it in this fashion. It is very misleading, because you can't have a determinant in which the first row consists of unit vectors and the other 2 rows consists of components of vectors. In a determinant, which is a proper determinant in the correct sense of the word, the nature of all the elements should be exactly the same. You can't have a determinant in which one row has one kind of element and another row has another kind of element or anything like that, mathematically speaking. So this is only a mnemonic. It is not a rigorous formula at all. It is easy enough to write down what the cross product is, because I know that if I have 2 vectors A and B, then the x component of the cross product is A2B3 minus A3B2, and then it is cyclic permutations of 1, 2, 3. So it is A3B1 minus A1B3 and then A1B2 minus A2B1, where I have called the vectors A and B. I have said the components are A1, A2, A3 and B1, B2, B3 instead of X, Y, Z. So it is easy enough to remember this and write it down, and I do not find that this is particularly helpful, but this is written down in elementary textbooks very often, but it is also misleading because it is certainly not a proper determinant at all. Okay. All right. Now the next thing we need is the following. We have seen what the geometrical meaning of A cross B is in terms of the area of a parallelogram. And the question we could ask then is, what is this quantity A dot B cross C? If you give me 3 vectors A, B and C in space, three-dimensional space, what is the meaning of A dot B cross C? Well, that is not very hard to figure out, because if these vectors are in this fashion, oblique for example, so here is A, here is B and that vector is C going into the board a little bit, then B cross C, as you know, is the area of this parallelogram, and you are dotting it with A, which means you are taking the projection of A along the direction normal to this parallelogram. But that in magnitude is precisely the volume of a parallelepiped formed from these vectors. Not very good at drawing this, but it is precisely the volume of this parallelepiped from A, B and C. So the magnitude of this quantity, because the sign of this quantity, it is a scalar, could be either plus or minus 1, but the magnitude of this quantity is equal to volume of parallelepiped formed from A, B and C. And when would it be 0? It would clearly be 0 if this dot product vanished. And when would it vanish? It would vanish if this vector was perpendicular to the vector B cross C. But what does that mean? B cross C is in a plane normal to the plane formed by B and C. And if this vector is perpendicular to it, it means it is back in the plane formed by B and C. So it is equivalent to saying that I have a parallelepiped in which the third vector, instead of sticking out of the plane formed by the first two, is in the plane itself. So the volume vanishes, the volume is identically 0. So in the case in which A, B, C are coplanar, this is identically equal to 0. Equal to 0 if and only if A, B, C are coplanar. That is a useful piece of information to know. We could also write down what are the components, what is the actual magnitude of this quantity here. We could write in terms of the components of A, B and C. So that is an exercise left to the student, to you. It is an easy exercise. So here it is, exercise. Write out A dot B cross C in terms of the components So write it out in terms of the components of A, B and C, which means you take A to be, let us write it as 1, 2, 3, A1, A2, A3, B is equal to B1, B2, B3 and C to be C1, C2, C3. These are the Cartesian components of any 3 vectors A, B, C. In general, take it to be non-planar in some arbitrary directions in space, and then write this combination out in terms of A, B and C. Write down what this volume of this parallelepiped is, okay, and verify the volume. So let us call it the volume of this parallelepiped. That is what this quantity is in magnitude, that this volume is proportional to a certain determinant formed from the components of A, B and C. So verify that this is proportional to A1, A2, A3, B1, or let us write it properly in this fashion, it does not matter, A1, A2, A3, B1, B2, B3, C1, C2, C3. So this so-called triple scalar product has a very simple geometrical meaning. It is related to the volume of the parallelepiped from these three vectors, and that volume in turn has a very simple expression in terms of the determinant formed by writing the column vectors down as column vectors next to each other and then taking the determinant of the result. Okay. So all these facts have important geometrical significance and a lot of practical use as well. Generalizations to higher dimensions, etc., exist. So this is something which is worth verifying, that the so-called triple scalar product is related to the volume, and the volume can be written in the form of this thing here. By the way, this is a reasonable thing, because you can already see in A dot B cross C, if you took the first component of it, the x component, so this is A1, and we want the one component of this, which is B2C3 minus B3C2, and indeed when you expand the determinant, you see you get A1 times B2C3 minus B3C2. So that is the first component already there. And now verify that the other two components add up to give you exactly this determinant here, up to a sign, up to an overall sign. Okay. The next thing we need to look at is what happens if I took the cross product of a cross product. So what is A cross B cross C? Again, I emphasize that while this might look like just playing around with vectors and doing vector algebra instead of doing serious physics, I would like to say again and again that the physics is buried in it. We are going to use all these things in physics at various places. This is very basic mathematics, and you need this for the proper understanding of physics. So what is this quantity equal to? Well, one way to do this would be very laborious. Write down the components. So write down first B cross C in Cartesian coordinates, and then write down A in Cartesian coordinates, and use the formula for the cross product of two vectors, and this should give you the answer completely. But now I would like to show you that there is no need to do that. You can actually use a much simpler trick to write this down, and it goes as follows. Again, I draw a little picture and say, suppose this is B, and that going inside is C, and that is some vector A. I would like to know what this quantity is. It is a vector. The answer is a vector. Now what I do know is that A cross any vector is perpendicular to the plane formed by A and that vector. So in particular it is perpendicular to A. Therefore this vector, whatever it is, cannot have a component along A, because it is perpendicular to it because of the cross product. Let us therefore call this vector D, and the argument is that D cannot have any component in the direction of A. It cannot have any component in the direction of B cross C either, but that is a little more complicated than saying it can't have any component along this vector here. Now in three-dimensional space, if I have three non-coplanar, non-collinear vectors, then the coordinates of any point can be written as some multiple of the unit vectors of the first direction, the second direction, and the third direction, independent of whether these directions are perpendicular to each other or not. I can use oblique coordinates in a plane or in 3 dimensions. So in general, I can write down the coordinate of any point, the position vector of any point I can express as a linear combination of numbers times the vectors B, C, and A in general. But now I am saying that this vector D cannot have any component along A. Therefore it can only have components along B and C, and therefore this answer must be B must be of the form something times B plus something times C, and these somethings must be scalars because the vector part is already taken care of by B and C. So this is a scalar and this is a scalar. Now what can these scalars be? Well, the left hand side here has an A to first power, and therefore the right hand side must also be linear in A. It has a B to the first power, so it must be linear in B. It must be linear in C. But there is already a B here. Therefore, this term here must be a scalar formed out of the other two vectors A and B, A and C. There is no other choice. So this must be a scalar from A and C, and this must be a scalar from A and B. Let us look at this first. What are the possible scalars you can form from two vectors A and C? Well, A dot A or A squared is one of them, C dot C or C squared is one of them, and A dot C is one of them. That is it. There are no other scalars which are independent which can be formed from two vectors A and C. Everything else is a function of these combinations. But this side, this quantity must be linear in A. If I multiply this left hand side, if I multiply A by 6, the answer must multiply by 6, and that only happens if it is linear in A here and linear in A here completely. Therefore, this is ruled out, that is ruled out, no nonlinear terms allowed. It has got to be A dot C, so this must be A dot C. And I put it in bracket to tell you that it is a scalar A dot C times P, but there is nothing to stop this from being square root of pi times A dot C or 18 times A dot C, we do not know. So there is some constant lambda times A dot C, absolute constant, because independent of what A, B, C are, this thing here must be the same number. It cannot depend on A, can't depend on C, can't depend on B. So therefore it has got to be a pure number, dimensionless number here. Similarly, the same argument says this must be A dot B and it must be multiplied by some number mu. So these are absolute constants, pure numbers, nothing to do with A, B, C or anything like that, like 2 pi or 4 or whatever. Okay. So that is a formula for D. Already we see the dependence on A, B, C is already explicit, and then there are two unknown numbers here. What do we do next? Well, we argue by saying that the way we constructed the cross product of two vectors was such that while two vectors B dot C gave a dot product which is the same as taking it in the other order C dot B, but B cross C is equal to minus C cross B. The cross product was antisymmetric under the exchange of the two vectors in the product, because we wrote the components down. We had things like B1 C2 minus B2 C1, and of course if you interchange B and C, the minus sign appears immediately in each of the components. So this is an antisymmetric product, this thing here is antisymmetric. We exploit that here, and if I interchange C and B, instead of B I write C, instead of C I write B, then I get exactly the same formula here, but wherever I got C I must write B, wherever I got B I must write C and put a minus sign. So this must be equal to minus lambda times A dot B C minus mu times A dot C. No other possibility. Again I go over the argument. Had I started with A cross C cross B by interchanging B and C, I would have got minus the original answer. D should go to minus itself. But D is given by this in the case of B cross C, and it is given by this in the case of the interchange. Now this is only possible, as you can see, these two must be equal to each other, and this is only possible if mu is equal to minus lambda and lambda is equal to minus mu. No other possibility. So it says, now we are almost home, it says that this quantity A cross B cross C must be equal to some constant lambda times A dot C B minus A dot B C. There is no other possibility where lambda is an absolute number, pure number. Okay. The next job is to find out what this number is. Well, for this now, since it does not depend on what A, B, C are, I use the fact that in the case of a simple choice like what if A, B, C are Cartesian unit vectors, I know that Ax cross Ey is equal to Ez and so on. So let me choose, for instance, without this is Exa, and let's choose this to be Ey and this back to be Ex. So A is Ex, B is Ex, C is Ey. Now what does this reduce then? We know that Ex cross Ey is equal to Ex cross Ez, because that is what Ex cross Ey is for this right handed triad, which is equal to minus Ey. So on the left hand side in this choice I get minus Ey, but I apply this formula and I get lambda times A dot C, but A was Ex and C was Ey, Ex dot Ey, B was also E sub x out here, minus A dot B. A dot B is Ax dot Ax and then C was Ey. This fashion. But Ex and Ey are perpendicular to each other. So Ex dot Ey is 0 and Ex is a unit vector. So Ex dot Ex is plus 1. So this side you get minus lambda Ey. So you have got the result that minus Ey is minus lambda times Ey, and that is not a very hard equation to solve. This implies of course that lambda is equal to 1 plus 1, and therefore we have a general formula for the vector triple product. By the way, this thing is called a vector triple product. We can be ready to write down what this formula is. Lambda has got to be 1, that is it, that is the formula. That is the formula for the vector triple product. And notice I did not use any special coordinate system. I did not write down the components of A, B and C and so on. I used extremely general arguments to find out that the answer can only be this, it can't be anything else in this fashion. Exercise. Use similar arguments to simplify A cross B dotted with C cross D. Take 4 vectors in 3 dimensions, A, B, C, D, arbitrary vectors. Find the vector A cross B, find the vector C cross D and take the dot product between the two. It is a scalar of course, and find what this is, and you get a formula similar to this except it is for scalars. This number here is a scalar, and use exactly the same sort of argument. The fact that the answer must be proportional to A, proportional to B, proportional to C, proportional to D, so it cannot be nonlinear in any of these vectors, magnitudes, and it must be a scalar at the end. So you need to know what are the possible scalars you can form from A, B, C and D other than their magnitudes squared, and the answer is of course you can form A dot B, A dot C, A dot D, you can form B dot C, B dot D and C dot D. So you have 6 possibilities and the answer must be a combination of these possibilities. So use this, it is an interesting exercise without going into components to simplify this combination here. Okay. So this is a little bit of vector analysis. What I will do next time is to go into dynamics. We are going to talk about what happens when you actually put in forces and so on, and we will try to write down the equations of dynamics, Newton's equations in vector form, and see how we can develop it further.